Two powerful types of linear voltage regulators and its applications. Linear voltage regulators are electronic devices used to maintain a stable output voltage level, irrespective of fluctuations in input voltage or changes in load current. They work by dissipating excess energy as heat to maintain the desired output voltage. Here's an overview of their applications and how they work. How linear voltage regulators work. Voltage regulation. Linear voltage regulators typically consist of a voltage reference, an error amplifier, a pass transistor, and feedback circuitry. The error amplifier compares the output voltage to a reference voltage and adjusts the pass transistor to maintain a stable output. Types of linear voltage regulators. Number 1 is fixed regulators are a type of linear voltage regulator that provide a constant output voltage regardless of changes in input voltage or load current. They are designed to maintain a stable output voltage at a specific predefined level. Here are some key features and applications of fixed regulators. Features. Predefined output voltage. Fixed regulators are set to provide a specific output voltage, which is determined by the internal circuitry of the regulator. Common fixed output voltages include 5V, 3.3V, and 12V, among others. Simple design. Fixed regulators have a straightforward design, typically consisting of a voltage reference, an error amplifier, a pass transistor, and feedback circuitry. This simplicity makes them easy to use in various electronic circuits. Low output voltage ripple. Fixed regulators provide low output voltage ripple, which is beneficial for applications requiring stable power supply voltages, such as in audio amplifiers or precision measurement equipment. Ease of integration. Fixed regulators are available in integrated circuit (IC) form, making them easy to integrate into electronic designs. They often come in standard package types like 220, 292, and surface mount packages. Applications. Consumer electronics. Fixed regulators are widely used in consumer electronics devices such as TVs, DVD players, set-top boxes, and gaming consoles to provide stable power to microcontrollers, sensors, and other components. Computers and peripherals. They are employed in computers, laptops, and peripheral devices like printers and scanners to regulate voltages for various components including logic circuits and communication interfaces. Power supplies. Fixed regulators are commonly used in low-power DC power supplies for hobbyists, educational purposes, and small electronic projects. Embedded systems. In embedded systems and microcontroller-based projects, fixed regulators are used to provide stable voltages to the microcontroller and other peripheral components. Industrial control systems. Fixed regulators are utilized in industrial control systems and automation equipment to regulate power supply voltages for sensors, actuators, and control circuitry. Instrumentation and measurement. They find applications in instrumentation and measurement equipment, ensuring stable voltage levels for accurate readings in sensors, data acquisition systems, and test instruments. Examples. LM7805. A popular fixed positive voltage regulator providing a stable 5V output voltage. LM7812, another commonly used fixed positive voltage regulator delivering a constant 12V output voltage. LM317, an adjustable linear voltage regulator that can be configured to provide various fixed output voltages. In summary, fixed regulators are essential components in electronic circuits requiring stable and reliable power supplies. Their simplicity, low output voltage ripple, and ease of integration make them suitable for a wide range of applications across different industries and electronic devices. Number 2 is adjustable regulators, also known as variable regulators, are a type of linear voltage regulator that allows the user to adjust the output voltage within a specified range. Unlike fixed regulators, which provide a constant output voltage, adjustable regulators offer flexibility in setting the desired output voltage level. Here's an overview of adjustable regulators, including their features, applications, and examples. Features. Variable output voltage. Adjustable regulators enable the user to set the output voltage to a desired level within a specified range. This flexibility makes them suitable for a wide variety of applications where precise voltage regulation is required. External feedback components. Adjustable regulators typically require external feedback components, such as resistors or voltage divider networks, to set the output voltage. These components are used to establish the feedback loop necessary for regulating the output voltage. Wide input voltage range. Adjustable regulators often have a wide input voltage range, allowing them to accommodate a variety of input voltage levels while maintaining a stable output voltage. Adjustable output current. In addition to voltage adjustment, some adjustable regulators also allow for the adjustment of output current limits, providing additional flexibility in power management. Applications. Lab power supplies. Adjustable regulators are commonly used in laboratory power supplies, where precise control over output voltage is essential for testing and prototyping electronic circuits. Battery charging. Adjustable regulators are employed in battery charging circuits to regulate the charging voltage, ensuring safe and efficient charging of batteries with different chemistries and capacities. LED drivers. They are used in LED driver circuits to provide a constant current or voltage to drive LEDs while allowing adjustment for different LED configurations and operating conditions. Analog circuitry. Adjustable regulators are used in analog circuitry where precise voltage regulation is required, such as in audio amplifiers, sensor interfaces, and data acquisition systems. Radio frequency (RF) circuits. They find applications in RF circuits where stable voltage levels are critical for the proper operation of transmitters, receivers, and RF amplifiers. Automotive electronics. Adjustable regulators are utilized in automotive electronics for various applications, including power management, lighting control, and sensor interfaces. Examples. LM317. A widely used adjustable positive voltage regulator that can provide output voltages ranging from 1.25 V to 37 V. LM337. A complementary adjustable negative voltage regulator to the LM317, allowing the generation of negative output voltages. Advantages and limitations. Advantages: flexibility in setting output voltage. Wide input voltage range. Suitable for a variety of applications requiring precise voltage regulation. Limitations: requires additional external components for voltage adjustment. May have higher output voltage ripple compared to fixed regulators, especially at higher output voltages. Lower efficiency compared to switching regulators, especially when the input-output voltage differential is large. In summary, adjustable regulators offer flexibility and precision in voltage regulation, making them suitable for a wide range of applications across different industries and electronic devices. Their ability to provide adjustable output voltages within a specified range makes them particularly valuable in scenarios where precise voltage control is required. Dissipation in the context of voltage regulators refers to the process by which excess energy is converted into heat and dissipated into the surrounding environment. This phenomenon occurs in linear voltage regulators due to the difference between the input voltage and the regulated output voltage, as well as the current flowing through the regulator. Here's how dissipation occurs in linear voltage regulators. Voltage drop across the regulator. Linear voltage regulators work by dropping excess voltage from the input to the output. For example, if the input voltage is higher than the desired output voltage, the regulator must reduce the voltage to maintain a stable output. This voltage drop results in energy dissipation in the form of heat. Current flow. The amount of current flowing through the regulator also contributes to dissipation. The regulator must pass the load current from the input to the output while maintaining the desired output voltage. As the load current increases, more energy is dissipated as heat within the regulator. Efficiency. Dissipation affects the efficiency of the voltage regulator. Efficiency is defined as the ratio of output power to input power. In linear regulators, where dissipation is significant, efficiency tends to be lower compared to switching regulators, which have lower dissipation losses. Heat dissipation mechanisms. Linear voltage regulators dissipate heat through various mechanisms, including conduction, convection, and radiation. The regulator's package and heat sinking mechanisms play a crucial role in dissipating heat effectively to prevent overheating and ensure proper operation. Heat sinks. In applications where dissipation is high, such as when the input-output voltage differential is large or the load current is high, external heat sinks are often added to the regulator to improve heat dissipation. Heat sinks increase the surface area available for heat transfer, allowing for more efficient cooling. Thermal shutdown. Some voltage regulators feature thermal shutdown protection mechanisms to prevent overheating. When the regulator's temperature exceeds a certain threshold, it shuts down temporarily to prevent damage, providing a safety feature in high-power or high-temperature environments. Overall, Dissipation is an inherent aspect of linear voltage regulators due to their operating principle of dropping excess voltage by converting it into heat. Understanding dissipation is crucial for designing efficient power supply systems and ensuring the proper operation and reliability of electronic devices. Power supplies are devices or systems that convert electrical energy from a power source into usable power at a desired voltage level for powering electronic devices or systems. They are crucial components in various applications across industries, providing the necessary electrical energy to power everything from small consumer electronics to large industrial machinery. Here's an overview of power supplies, including their types, components, and applications. Types of power supplies. Linear power supplies. Utilize linear voltage regulators to convert AC or DC input voltage to a regulated DC output voltage. Generally simpler in design and construction compared to switching power supplies. Suitable for low-power applications and where low noise and high stability are critical. Switching power supplies. Switch mode power supplies. Convert input voltage to a regulated output voltage through high-frequency switching and energy storage components. More efficient than linear power supplies, especially in high-power applications. Commonly used in various electronics, including computers, telecommunication equipment, and industrial machinery. Uninterruptible power supplies, UPS. Provide backup power during mains power outages or voltage fluctuations. Typically consist of a battery, inverter, and charging circuitry. Critical for maintaining continuous power supply to sensitive equipment, such as computers, servers, and medical devices.
YSRS converter.
Convert one DC voltage level to another DC voltage level. Used in applications where the input and output voltages need to be adjusted, such as in portable electronics and automotive systems.
Actinis i centens converters.
Convert AC voltage from the mains power supply to DC voltage. Found in virtually all electronic devices that require DC power, including household appliances, consumer electronics, and industrial equipment. Components of power supplies. Transformer converts AC voltage from the mains power supply to a different voltage level in AC-DC converters, or isolates the input and output circuits in linear power supplies. Rectifier converts AC voltage to pulsating DC voltage. Filter capacitors and inductors. Smooth out the pulsating DC voltage to reduce ripple and noise. Voltage regulators. Maintain a stable output voltage by regulating the input voltage or adjusting the duty cycle of the switching waveform in switching power supplies. Control circuits. Control the operation of the power supply, including voltage regulation, current limiting, and protection features. Output connectors. Provide connections for delivering the regulated power to the load. Applications of power supplies. Consumer electronics. Power supplies are used in devices such as smartphones, TVs, computers, and home appliances. Industrial automation. Power various industrial machinery, control systems, and sensors. Telecommunication equipment. Power networking devices, base stations, and communication infrastructure. Medical devices. Provide power to diagnostic equipment, life support systems, and medical imaging devices. Automotive electronics. Power electronic systems in vehicles, including engine control units, infotainment systems, and lighting. Renewable energy systems. Convert energy from solar panels, wind turbines, and other renewable sources into usable electrical power. In summary, power supplies play a critical role in powering electronic devices and systems across a wide range of applications. Understanding the different types, components, and applications of power supplies is essential for designing efficient and reliable power supply solutions for various industries and end users. Signal conditioning is the process of modifying an analog signal to prepare it for processing by subsequent electronic circuits or systems. It involves various techniques to enhance the quality, accuracy, or compatibility of the signal with the requirements of the downstream components. Signal conditioning is essential in many applications where sensors or transducers generate analog signals that need to be processed or analyzed by electronic systems. Here's an overview of signal conditioning, its techniques, and applications. Techniques of signal conditioning. Amplification. Amplifying the signal to increase its magnitude, thereby improving the signal-to-noise ratio, SNR. and ensuring that it falls within the dynamic range of the subsequent circuitry. Operational amplifiers, op-amps, are commonly used for signal amplification. Filtering. Filtering removes unwanted noise, interference, or frequency components from the signal. Low-pass, high-pass, bandpass, and bandstop filters are employed to shape the frequency response of the signal according to the application requirements. Linearization. Some sensors, such as thermocouples or strain gauges, may produce nonlinear output signals. Signal conditioning techniques can include linearization algorithms or circuits to convert these signals into linear responses. Isolation. Isolation techniques protect sensitive circuitry from potentially damaging effects, such as voltage spikes or ground loops, by providing electrical isolation between input and output circuits. Attenuation. Reducing the signal magnitude to prevent overload or saturation of downstream circuitry. Voltage dividers or variable attenuators are often used for this purpose. Impedance matching. Ensuring that the impedance of the signal source matches that of the subsequent circuitry to minimize signal distortion and maximize power transfer. Temperature compensation. Compensating for variations in signal characteristics due to temperature changes, particularly important in sensor applications where temperature fluctuations can affect signal accuracy. Signal conditioning ICs. Integrated circuits specifically designed for signal conditioning purposes, offering various functionalities such as amplification, filtering, and analog-to-digital conversion in a single package. Applications of signal conditioning. Sensor interfaces. Signal conditioning is extensively used in sensor applications to condition the output signals of sensors such as temperature sensors, pressure sensors, accelerometers, and strain gauges for further processing or measurement. Data acquisition systems. Signal conditioning is an integral part of data acquisition systems, where analog signals from sensors or transducers are conditioned, digitized, and processed by a microcontroller or computer for monitoring or control purposes. Industrial automation. In industrial automation, signal conditioning prepares analog signals from various sensors for use in control systems, monitoring equipment, and feedback loops. Communication systems. Signal conditioning is used in communication systems to prepare analog signals for transmission or reception, ensuring compatibility with modulation/demodulation schemes and noise immunity. Medical instrumentation. In medical devices and instruments, signal conditioning ensures the accuracy and reliability of physiological measurements obtained from sensors such as ECG electrodes, blood pressure sensors, and oxygen sensors. Automotive electronics. Signal conditioning is employed in automotive applications for processing signals from sensors used in engine control systems, vehicle diagnostics, and driver assistance systems. Environmental monitoring. Signal conditioning is utilized in environmental monitoring systems for conditioning signals from sensors measuring parameters such as humidity, gas concentration, and radiation levels. In summary, signal conditioning plays a crucial role in preparing analog signals from sensors or transducers for further processing, analysis, or transmission in a wide range of applications across industries such as manufacturing, healthcare, communications, and automotive. It ensures signal integrity, accuracy, and compatibility with downstream electronic systems, thereby enhancing the performance and reliability of the overall system. Audio amplifiers are electronic devices used to increase the amplitude of audio signals for driving loudspeakers or headphones, thereby producing sound. They play a crucial role in audio reproduction systems, ranging from small portable devices to high-fidelity stereo systems. Here's an overview of audio amplifiers, including their types, components, and applications. Types of audio amplifiers. Analog amplifiers. Traditional amplifiers that use analog circuitry to amplify audio signals. Classified based on their operating class, such as Class A, Class AB, and Class D amplifiers. Class A amplifiers. Operate in a mode where the output transistors conduct continuously throughout the entire cycle of the input waveform. Known for their high linearity and low distortion, but are less efficient and generate more heat compared to other classes.
Class AB amplifiers.
Combined features of Class A and Class B amplifiers, with output transistors conducting for more than half, but less than the entire cycle of the input waveform. Offer improved efficiency compared to Class A amplifiers while maintaining good linearity and low distortion. Class D amplifiers, digital amplifiers. Utilize pulse width modulation, PWM, or pulse density modulation, PDM, techniques to amplify audio signals. Highly efficient, making them suitable for battery-powered devices and high-power applications. Components of audio amplifiers. Input stage. Receives the audio signal from the source device and typically includes coupling capacitors to block DC voltage. Amplification stage. Amplifies the audio signal to the desired level using active components such as transistors or operational amplifiers, op-amps. Tone control circuitry. Optionally includes bass, treble, and mid-range control circuits to adjust the frequency response of the amplifier. Volume control. Adjusts the output level of the amplifier to control the loudness of the audio. Feedback network. Provides stability and improves linearity by feeding a portion of the output signal back to the input. Output stage. Drives the loudspeakers or headphones and includes output transistors or integrated circuits capable of delivering sufficient power to the load. Applications of audio amplifiers. Home audio systems. Powering speakers and stereo systems, surround sound systems, and home theater setups. Public address, PA, systems. Amplifying audio signals for announcements, music playback, and addressing audiences in public venues, stadiums, and concert halls. Musical instruments. Amplifying the sound produced by electric guitars, keyboards, and other musical instruments. Car audio systems. Powering speakers and subwoofers in car stereo systems for in-car entertainment. Professional audio equipment. Amplifying audio signals in recording studios, live sound reinforcement setups, and DJ equipment. Personal audio devices. Powering headphones and earphones in portable media players, smartphones, and laptops. Key considerations in audio amplifier design. Power output. Sufficient power output to drive the intended speakers or headphones at the desired volume level without distortion. Frequency response. Flat frequency response across the audible spectrum to reproduce audio accurately. Signal-to-noise ratio, SNR high SNR to minimize background noise and ensure clear audio reproduction. Distortion. Low distortion to maintain the fidelity of the original audio signal. Efficiency. Efficiency considerations, especially in battery-powered devices, to maximize battery life. In summary, audio amplifiers are essential components in audio reproduction systems, providing the necessary amplification to drive speakers or headphones and reproduce sound accurately. Understanding the types, components, and applications of audio amplifiers is crucial for designing and implementing high-quality audio systems across various domains. Instrumentation and measurement refer to the process of acquiring, analyzing, and interpreting data from physical phenomena or systems using specialized instruments and techniques. This field encompasses a wide range of applications across various industries, including scientific research, engineering, manufacturing, healthcare, and environmental monitoring. Here's an overview of instrumentation and measurement, including its key concepts, instruments, and applications. Key concepts. Measurement. The process of quantifying physical quantities or parameters, such as length, temperature, pressure, voltage, current, and frequency, using appropriate measuring instruments. Instrumentation. The art and science of designing, developing, and deploying instruments and measurement systems to acquire accurate and reliable data. Sensors and transducers. Devices that convert physical quantities into measurable electrical signals. Sensors detect physical phenomena directly, while transducers convert one form of energy into another, typically electrical signals. Data acquisition. The process of collecting and digitizing analog signals from sensors or instruments for storage, analysis, and display. Signal conditioning. Techniques used to modify and pre-process analog signals to improve their quality, accuracy, and compatibility with measurement systems. Calibration. The process of adjusting and verifying the accuracy and precision of measuring instruments by comparing their readings to known standards. Data analysis and interpretation. Analyzing acquired data to extract meaningful information, identify trends, anomalies, and patterns, and draw conclusions about the underlying physical processes or systems. Instruments and measurement techniques. Multimeters, versatile instruments for measuring voltage, current, resistance, and other electrical parameters. Oscilloscopes, instruments used to visualize and analyze the waveform of electrical signals over time. Sensors and transducers, including temperature sensors, pressure sensors, strain gauges, accelerometers, flow meters, and many others, each designed to measure specific physical quantities. Data loggers, devices used to record and store data over time, often used in environmental monitoring, industrial process control, and scientific research. Spectrometers, instruments used to measure the intensity of light at different wavelengths, commonly used in spectroscopy and optical analysis. Gas chromatographs, instruments used to separate, identify, and quantify the components of complex mixtures of gases. Medical instruments, including blood pressure monitors, electrocardiographs, ECGs, and imaging equipment used for diagnostic and monitoring purposes in healthcare. Applications: industrial process control, monitoring and controlling parameters such as temperature, pressure, flow rate, and chemical concentrations in manufacturing processes to ensure product quality and safety. Environmental monitoring, measuring air and water quality, pollutant concentrations, and environmental parameters to assess and mitigate the impact of human activities on ecosystems and public health. Automotive testing and diagnostics, analyzing engine performance, emissions, and vehicle dynamics to improve fuel efficiency, reduce emissions, and ensure vehicle safety and reliability. Scientific research, conducting experiments, collecting data, and analyzing results in fields such as physics, chemistry, biology, and materials science to advance scientific knowledge and understanding. Healthcare and biomedical engineering, monitoring physiological parameters, diagnosing diseases, and assessing patient health using medical instruments and diagnostic imaging techniques. Aerospace and defense, testing and monitoring aircraft systems, spacecraft components, and military equipment to ensure performance, safety, and reliability in harsh environments. Energy and utilities, monitoring power generation, transmission, and distribution systems, as well as energy consumption and efficiency in buildings and industrial facilities. In summary, instrumentation and measurement play a critical role in virtually every aspect of modern life, from scientific research and industrial manufacturing to healthcare and environmental protection. Advances in instrumentation and measurement technologies continue to drive innovation and improve our understanding of the world around us while enabling better decision-making and problem-solving in a wide range of applications. Here are some advantages of instrumentation and measurement. Precision. Modern instrumentation allows for highly precise measurements, enabling scientists, engineers, and researchers to quantify physical phenomena with high accuracy. Automation. Automated measurement systems can perform measurements continuously and reliably without human intervention, increasing efficiency and reducing human error. Real-time monitoring. Instruments equipped with real-time monitoring capabilities allow for immediate feedback and response to changes in measured parameters, facilitating rapid decision-making and control. Data acquisition. Advanced data acquisition systems can capture and store vast amounts of data quickly, enabling comprehensive analysis and insights into complex systems and processes. Process optimization. Measurement data can be used to optimize industrial processes, improve efficiency, reduce waste, and enhance product quality. Quality control. Measurement systems are essential for quality control in manufacturing, ensuring that products meet specified standards and requirements. Safety. Monitoring and measuring critical parameters in various environments, such as industrial plants, medical facilities, and transportation systems, contribute to maintaining safety and preventing accidents. Environmental monitoring. Instruments for measuring environmental parameters help assess and mitigate environmental impact, monitor pollution levels, and ensure compliance with regulations. Healthcare. In healthcare, precise measurement instruments aid in diagnosis, treatment monitoring, and patient care, contributing to improved health outcomes. Research and development. Measurement instruments play a crucial role in scientific research and development, providing valuable data for understanding natural phenomena, developing new technologies, and advancing knowledge in various fields. Predictive maintenance. Monitoring equipment condition through measurement techniques allows for predictive maintenance, reducing downtime, and extending equipment lifespan. Cost reduction. Effective measurement systems can lead to cost savings by optimizing processes, reducing waste, improving efficiency, and preventing equipment failures. Overall, instrumentation and measurement offer numerous advantages across various industries and applications, ranging from enhancing precision and efficiency to improving safety, quality, and environmental sustainability. These advantages contribute to better decision-making, innovation, and progress in diverse fields of science, engineering, healthcare, and beyond. While instrumentation and measurement offer numerous advantages, there are also some disadvantages associated with these processes. Here are several considerations. Cost. High-quality measurement instruments and sophisticated data acquisition systems can be expensive to purchase, operate, and maintain, especially for complex applications or specialized requirements. Complexity. Setting up and calibrating measurement systems often requires technical expertise and specialized knowledge, making them challenging to deploy and manage, particularly for non-experts. Calibration and maintenance. Regular calibration and maintenance are essential for ensuring the accuracy and reliability of measurement instruments, which can be time-consuming and costly. Data overload. Advanced measurement systems can generate large volumes of data, leading to data overload and making it challenging to extract meaningful insights without suitable data analysis tools and techniques. Interference and noise. Measurement accuracy can be affected by external interference, noise, or environmental factors, requiring careful shielding, filtering, or compensation techniques. Limited resolution. Some measurement instruments may have limited resolution or sensitivity, leading to inaccuracies or uncertainties in measured data, particularly in low-level signals or small variations. Response time. Instruments with slow response times may not capture rapid changes or transient events accurately, limiting their suitability for dynamic or high-speed measurements. Maintenance downtime. Scheduled maintenance and calibration activities can result in downtime for measurement systems, disrupting operations and potentially impacting productivity. Compatibility issues. Integrating different measurement instruments or data acquisition systems from different manufacturers can lead to compatibility issues, requiring additional effort to ensure interoperability and data consistency. Operator error. Human error, such as incorrect setup, operation, or interpretation of measurement data, can lead to inaccuracies or misinterpretations, compromising the reliability of measurement results. Limited range. Some measurement instruments may have a limited range or dynamic range, restricting their applicability to specific measurement tasks or operating conditions. Ethical considerations. In some cases, measurement activities may raise ethical concerns, such as invasion of privacy, surveillance, or environmental impact, requiring careful consideration and ethical oversight. While these disadvantages exist, they can often be mitigated through careful planning, proper training, and the use of appropriate technologies and methodologies. Despite the challenges, the benefits of instrumentation and measurement generally outweigh the drawbacks, contributing to advancements in science, technology, industry, and society as a whole. In summary, linear voltage regulators are essential components in various electronic circuits where stable and low-noise power supply is required, although they are less efficient compared to switching regulators, especially in high-power applications.